So this is the 3-9 beta lesson. I'm just going to remind you, this is where we left off on Monday. This is exponential, okay? The derivative of a to the x. Well, that's the big picture. You know the derivative of a to the x, the derivative of e to the x, it's a subset of that. So the derivative, I'm not going through all this, you can follow it. And if you have a question, then ask the question. But the point is, this takes us to here. The derivative with respect to x, this x does not match up with that exponent. It's exponential function. You have to do this implicitly. That's what you're looking for. Do those variables match? Gives you itself, just like e to the x gives you itself, times the natural log of the base times the derivative of the exponent. So here's an example. This problem was on, here's e to the x, why that works. This problem, 3 caret pi x, was on some multiple choice test, AP test, or this. Look at the test. That was a May question, right? This is just, now, oh, this is easy. It's easy today because we're doing this right now. We could go ahead to May, when you're reviewing 7 chapters of material, it's not so easy. We have to realize that this is a subset of that. So the derivative of this would be itself times the natural log of the base times the derivative of the exponent. Derivative of the exponent, derivative of pi times x would just be pi. So your answer would be 3 to the pi x times ln 3 times pi. If you see that, that's logical to you, that you're current through what we did on Monday. And again, you have access to this PDF, so you don't feel like you need to write this down. Remember, so I get it. Seeing the board, I'm not a big fan of this display, but I can assure you, I've been in the building. The boards in the building are really fine. You want to make more issues straining to see stuff from where you are in the room, right? So now we're going with the inverse function. If I look at this, I go over here and say, here's the alpha lesson. The alpha lesson is y equals e to the x. The general case is a to the u. It's an exponential function. It's growing exponential. What we're doing in the beta lesson is taking whatever that curve is and reflecting it over the line y equals x. So it's the inverse function. So if this was e to the x, the blue curve would be ln. What we're trying to do is find the slope of the curve. Just like you try to find the slope of the curve on Monday. So I'm referring you to the derivation of the book on page 174. Without retyping it. Let's find the derivative of ln x. Again, this is a subset of the general case. So the derivative of the natural log of x, I have y equals ln x, which is the inverse function of y equals e to the x. Another way to write that is x equals e to the 1. So if x equals e to the y, we're going to differentiate that. Now on the right side, it's user-friendly because you're finding the derivative with respect to x of x, which is just a 1. On the left side, you have to do this implicitly because you're finding the derivative of e to the y with respect to x. And those variables don't match. So this is back to section 37. So you would get itself times dy dx, which is what we're trying to get. Divide both sides by e to the y. E to the y equals x. So you would just get 1 over x. The derivative of the natural log of x is 1 over x. What does that mean? It means if I come over here to this picture, my H chart looks like this. I have x, I have y equals ln x, and y prime equals 1 over x. So on this picture, if I go 2 to the right, I would get the natural log of 2. As the natural log of 2, the slope would be 1/2. And the tangent line would be y equals 1/2 x slid to the right up ln2. Well, that's a constant. So the tangent line would be y subtract ln2 equals 1/2 x subtract 2. This is 100% consistent with what you've done the entire first marking group. This is the big, like if this table right here, in this pre-image and translation to get the image, it's going too fast for you that you write this down. This helps you not just today, but everything came up till here. This is just one example of stuff we've done through the entire chapter. We have an input, output, and instantaneous change. The instantaneous change is the slope of the curve. To get the tangent line, y equals 1/2 x is off the origin. So we're clicking and dragging it to the point, this takes 2 ln. Then if we go over here, the natural log of mu would be 1 over mu dv. Good? Then on the next page, here's the most general case. Not ln, but log some other base other than e. Log base a of x. Now, property of logarithms, whether you recognize it or not, this can be rewritten as ln x over ln a. It goes back to algebra 2, really, property of logarithms. And now what? Differentiate both sides. We're going. ln a is a constant, so they bring that out. I'm derivative of ln x, which you just did, and you get this. And the general case of the mu is down here. There is a summary at the end of the PDF comparing the alpha and beta lessons. But right now, we're just trying to get our mind around the big picture, which really goes with what's on the board. So, here's what was in the book on pages 174 and 175. 174, how do you get the derivative, ln x, which is a subset of the derivative of ln mu. Page 175, this is a subset of this, because it could be log base e, which is what ln is an abbreviation for. But this is more general. This is here, this is here. This is the most general case. Second row, second column. Second row, second column is the derivative with respect to x of log base a of mu. So if this thing were ln x, ready? you'd have 1 over x times the natural log. The base would be e, or ln. The natural log of e is 1. So you have 1 over x times the derivative of the exponent, which would be a 1. Or the derivative of this, I'm sorry, this term, which would be a 1, and you would just get back to there. Example 4. Now, example 4 is kind of silly. We're on page 175 of your book. You may say, if you were to paste all this stuff, we're not going to get through the whole thing. If you were to paste this question, it'll show you that this, like substitute values. It'll take you to the answer. Well, we know what the answer is. The question is, find the derivative if y equals log base a of a to sine x. What exponent can you raise a to give you a to the sine of x? What exponent do you raise a to? So you end up with a raised to sine x. It's not a trick question. Sine x. Thank you. So the question says, it's a fancy way of saying, what's the derivative of y equals sine x? If you look down here, you get cosine x. All they're doing in these 3 lines is showing you end up with the same thing. You wouldn't do that one. You would simplify the question to get sine and derivative of sine cosine. But these are the steps. It's using this tan box. So leave that tan box there, and we'll ask you to go to problem 23. All right, so here's what we got. Went over here and said mu is x to the negative 1. So the derivative of mu with respect to x would be negative 1 times 1 over x squared. Now what? I have log base 2 of mu. What do you get? 1 over the natural log, the base, times 1 over mu. 1 over x to the negative 1 is essentially x. 1 divided by 1 over x, and we're going to multiply, times this derivative. So you have an x up here, which reduced with one of the x's in the derivative. I'll just leave you with an x. Negative 1 divided by x ln 2. And x has to be positive. And the derivative has to be positive, because if you go back to the question, you can't, the restriction on the domain is x has to be positive, because if you look at the picture, your input can't be negative. There is no exponent you raise 2 to give you a negative value. All right? But to be honest with you, right now, I'm not as worried about the domain as I'm worried about the substituting in the calculation. So how about example 7? Same type of problem. We have this, y equals x caret x. So here's the only issue. In order to do that, you need a prompt. And the prompt is, take the natural log of both sides before you start. How would I know to do that? Well, if you do a few homework problems, you would see it by repetition. Well, why would you do that? Because property of logarithms allows me to bring this x out front. So the natural log of y equals x ln x. Take the derivative of both sides. We already did this. That's going to give you ln y dy dx. The right side is going to give you the product rule. The derivative of the first term is 1 times ln x, plus the first term times the derivative of ln x is 1 over x. These would give you 1. Multiply both sides by y times this. What's y equal? Y equals x caret x. So this mess right here would be the slope of x caret x. Now, what's going to happen is this. If you are in the room, we're going to take you to the corresponding problem for the exercise. If you're at home, then you're leaving to go to AP classroom to do the exit ticket. I don't want people racing through that. Okay? So, we'll leave this up here, and you're going to problem number 443. Right? It was the same technique in the example. You take the natural log of both sides. Then you bring this exponent out front as a coefficient. Same thing as in the example on the left. On the right, that's what? That's the product rule. So I took the derivative of the first term. Well, I took x first. It doesn't matter. It's the commutative property of addition. You can have this plus that. It's the same thing. So you have this times this plus, sorry, derivative of this times this plus this times the derivative of ln sine x, which is 1 over mu d mu. 1 over sine x times the derivative of sine, which is cosine. Cosine over sine is cotangent. And then right here, from here to here, we just rewrote what y is equal to. Y equals sine x caret x. So you look at this and say, okay, well, we knew we were going to take the natural log of both sides. All right. And we knew property of logarithms would bring this x out front. We just did this. So everybody should have been down to the left side of line 4. To the right side of line 4, if you got stuck by the product rule, then you got to look at your work and compare it to what it should look like. Oh, I didn't write cotangent. I wrote cosine over sine. That'd be fine, but that's the way it's going to look like in a multiple choice scenario. So that's on the PDF. Last thing, this is the summary of the alpha and beta lessons. And the point is, the top lines are what matters. Because everything else is a subset of the top line. So the derivative of a to the mu from the alpha lesson, the derivative log base a of mu from the beta lesson. And how the derivative of e to the x is a subset of this, the derivative of ln x is a subset of that. So, ready? The derivative of e to the x is itself. The derivative of ln x is 1 over x. Okay, they're pretty straightforward. Except you'll never get those questions in May. You'll get these questions up here. So if you look at the top line and make an effort to get around your mind around that, then these that last row is just a subset of that. So that's it for the beta lesson.